reflections that affect the x-axis or about the x-axis, and we have reflections about the y. So if it was about the x-axis, let's think about it. If this is my x-axis and I reflect about the x-axis, which is being negated, my x's or my y's? I was up here, I am now down here. What's being negated? Y's. And a y-axis, if I'm over here and I'm now over here, what's being negated? My x's. So when I actually say a reflection in the y-axis, what is it affecting? The x's. And a reflection in the x-axis actually affects the y's. So it's the opposite of the axis, right? Because if you have an x-axis, your y, if it's like 0, 3, it's now going to be 0, negative 3. My x didn't change at all, right? Okay. So, a reflection is a mirror image about a line or an axis. Invariant points are points that do not move. This is important because you will often get asked about invariant points. Invariant points are ones that don't move. They do not change. They never change. So sometimes a point exists and I apply a whole bunch of transformations and that same point still exists, but it moved here and here and here and then came back, right? So it actually moved to get itself back to that same spot. It was a different point and it landed onto that spot. Okay? One down here, end up here. That's not invariant. Invariant is the point was here, I did a whole bunch of transformations, and it stayed. It didn't move, ever. Not this point moved on top of that one that existed already. Okay? So we're going to have a reflection in the x-axis, and that affects the what? Affects the y values. Because in order to reflect in the x-axis, your y values have to be negated. Yes? Okay. So, how does that look on an equation? Well, if it affects the x's, it would have to be in with the x, right? Is anything in with the x? No. So if it's not in with the x, it affects the y's, right? That's the easiest way to think about it. If it's in the bracket with the x, it affects the x's. If it's not in that bracket, and it's anywhere else, it affects y's. And y's never change, so life is good. All right. So this is the original. The original is just any function in the world, right? Y equals f of x. We don't know what it looks like currently. It's just any function in the world, right? And now I'm going to do this to it. Well, the negative is here. Is that in the bracket with the x? No, so that affects the y's. And if it affects the y values, it's a reflection in the x-axis. It's in the opposite axis. Because in order to affect my y's, it has to be in the x-axis. In order to affect my x, it has to be in the y-axis. Yes? Right? Okay. So, we're going to look at this one. It says the graph of y equals x squared minus 4x plus 4. Can you guys type that into your calculator, please? X squared minus 4x plus 4. Yeah.
Someone does not have a calculator. Could you use one of yours?
Oh, yes, he could. You know what would be great? Brady is going to ask. But you know what? Beggars can't be choosers. And we just accept, we just are happy we get someone asking, right?
Yes.
Yeah. Your, like, 1942 calculator doesn't graph?
Unfortunately not.
Oh, darn it. Yeah. X squared. All right. So, we're going to graph it. Shh. Everyone paying attention, because some people, I find, don't use graphing calculators as much as others. Some people overuse graphing calculators and don't know how to do algebra. So there's this nice little fine-tuned middle. We're going to get ourselves there. So we can graph this using our calculator. Now, what I would want to do is start at like standard window. You guys might be at crazy windows because who knows the last time you've used this. So your standard window for graphs, except for trig, is zoom 6. Zoom is your top middle button. 6 gets you your standard window back. So it's that negative 10, 10, negative 10, 10 window. Can we see the graph? Yeah. Okay, cool. Now, we can go trace. Do you see how there's that trace button? And no second trace, just that trace button? We could use that. I would suggest you flash freeze that and never use it. Like pretend it doesn't exist. It's not accurate. I see a whole bunch of people using it all the time. They're like, I just traced it. I got close to the vertex. It was close. It's close. It's close to the vertex. No. So that trace button, that just the bold, press it. Don't. Now second trace is where we want to live for most of our lives. So we're going to try that out. We're going to go second trace. Because whenever we press the second button, the word above that button is what we're doing. So what are we doing currently? Calculating something. I want to calculate the vertex. Vertex isn't in here. But what is another word for vertex on this one? Yeah. Minimum or maximum. In this case, it's a minimum. So we're going to go to 3. Now it says what it says. It says what on it? Left bound. So we need to be on the left bound of whatever we're finding, right? If I was finding an x-intercept, I have to be on the left of that. So whatever you press, this time I press minimum. So I need to be on the left of it. So I go to the left somewhere, anywhere on that left, and I hit enter. Then what does it say? Right bound. So now I need to hold my right cursor till it's somewhere on the right side, and I hit enter. And then it says guess. I don't know why it does this. I wish they would have programmed that out, but that just means you need to press the button again, because it's going to do some work for you. Voila! What's our vertex, or our minimum? 2, 0. So I'm just going to plot here, and then guess what? Because you know it's supposed to be 2, 0, you obviously know my scale. No, I'm once again getting marks and you're not, if you don't tell me what the scale is. So I want to make my x scale 1. So I write x scale 1. So that means every single tick is 1. I don't have to write 1, 2, 3, 4 in tiny numbers underneath. Not only do I not have to, you shouldn't. It gets all messy and mumble jumble, right? So that's x scale, and then this would be y scale. And we're going to make that one be 1 as well. You don't have to have your scales be the same. Your x scale could be 1 and your y scale could be 10, right? If the graph grows really fast like an exponential function, it might be 1 in 100 or whatever. Okay? All right. Now we can go second graph and pull values off our table. So I'm going to look for 2, 0 because that's the vertex, and I'm going to start plotting stuff around it. So I have 2, 0, then I have 1, 1, and I have 3, 1, 0, 4, and then 5 and 9. And then I extend my arrow out a little bit. Now, what does a bad graph look like? Oh, I've seen many a bad graph. I see bad graphs more than I see good graphs. It makes my heart drop a little bit. What you guys will do is you'll draw, okay, this point, this point, this point, and then you're like, and send it to the world, and go, offload. Guess what is accurate on this graph? That. That is all that is accurate. So what really, if you draw those 3 points, if you want to draw an arrow, it has to be here, a little bit after. And then you should be like, wait a second, but then there'd be no graph up here, and I get in trouble for not having enough graph. True. So what should you have more of? Dots. Not good graph. Amazing graph. Yes. Okay. More coordinates, happier Mrs. Lepp will be. Okay? You just want to make me happy. I know you do. Right? It's easy. It's true in life. Okay. So, if I were to do this now, what did we say that was? That affects the what values?
Y.
Y values. If it affects my y values, that means whatever's positive will be negative. Whatever's negative will be positive. What axis am I going around? The x. So, we're going to write reflection. Reflection in the x-axis. VIP, that's me, very important person. You should pay attention. I tried to caca, that wasn't even English. Levi, that's you. Oh my gosh, he's gonna have to go in the other direction because he's not getting it, you know, he's backwards. I blame the backwardsness of it. You gotta give him a hand signal, Ian, like this, just.
I was like, him.
No, not a hand signal. That's not a hand signal. That's just hitting. Like, I mean, like, you go like this to yourself. Not like this to Levi, but like to yourself. Just take a hand. All right. Yeah, hand signal hitting, very different. Hand signal staying with you. If you actually connect with someone, that's a hit. Very different. All right. Okay. So I wanted to reflect in the x-axis. So every single one of my y values is not going to negate. So my mapping would be xy becomes x negative y, right? True statement?
Sure.
Now I could go along here and I could go, okay, this is -1 and 9. It's going to become what? -1 and -9. So it's going to be down here. Then I have 0, 4. It's going to become peanut gallery. I'm not going to say table anymore. I'm just going to say peanut gallery. Because that's what you want. All right. 0 and -4. The peanut gallery is going to get moved to desks, and the desks are going to get moved to the table. It's going to be really weird and awkward. Okay. 1 and -1. And then we have 2, 0. What happens with 2, 0? 2 and -0, is there such a thing? It stays the same. What might we call that? Invariant. Amazing what you can learn when you listen. No, it's crazy. Right? Okay. Peanut gallery. So we have 3, 1. It's going to become 3, -1. And then this one's going to reflect down here, and this one's going to reflect down here. So when we negate our y values, we reflect in the x-axis. True? Make sense? Up, you're now down. If some of it was below and some of it was above, it would still reflect. Yeah. So the mapping, remember I told you that you're going to want to not, and you're going to be like, I'm so smart, I don't have to do that. But then I said that you can practice it.
This is what you like.
Not if it says show work. And we're practicing for 4 days from now, when it's Monday, Tuesday, when it's going to be aggressively harder. Because we're going to have everything together. We're practicing it now. Like, thoroughly. I don't want to. Okay. All right. So we have to write the equation of that. So what we would do is this is negative f of x, correct? So we're going to replace f of x with this, because this is what f of x equals, yes? So we're going to say y equals negative f of x, x squared minus 4x plus 4. And we distribute our negatives, so we get y equals negative x squared plus 4x minus 4. And yes, you could put that one in and graph it, but then it wouldn't show what we're all trying to show. Okay? State the coordinates of the invariant points. Well, it's just 2, 0. Why is it invariant? What are you doing in the mapping? Yeah, but why? What are we doing to all of our y values? We're multiplying them by -1, correct? What happens when you multiply a 0 by anything? It stays the same. So if your transformation is a multiplication, wherever y is 0, it's going to stay, because when you multiply by 0, it stays, right? So in this case, where do the invariant points exist? On the x-axis. Because we're reflecting in it, correct? So if we reflect in the x-axis, the only place that's not going to reflect is the actual x-axis. That's your reflecting point. Wherever the mirror image is where it doesn't reflect. But y, it's on the x-axis since the y values are all 0. And multiplying by -1 will remain 0. And then how does the graph of negative f of x compare? It's a reflection in the what? X-axis. If it affects the y, it's a reflection in the x-axis. Example 2 says the graph of y equals f of x is shown. Sketch the graph of y equals negative f of x. If I'm sketching a graph, I'm moving coordinates. If I'm moving coordinates, what do I use? Starts with an M. Mapping. Every single time. So I'm going to bold this point. I need at least one on this arm, the point, and one on this arm, correct? What's my mapping going to be if it's negative here? Which one's going to be negative, x or y? Y, because what's with my x? Brackets. A 1. Nothing really, right? So it's going to be xy becomes x negative y. Please use mapping on those 3 points. Graph the graph. Go. So we take our first coordinate. It's at -4, 0. We put it into the original because it's the original coordinate. And then it becomes -4. What? It's invariant because it's on the x-axis. True statement. All right. Our next one. We have 1 or -1 and 4. It's going to become -1 and -4. And then we connect them so that we don't mess up and mix up. Now, do you see how I drew the arrow a little past, but I didn't have to stop? If I want more accurate, I'm going to have to pull more points. And then this one here is 1, 0. It's going to become 1, 0. This one and this one are here. And that line does not have a curve. And I don't know why I did black since the graph was black already. That was dumb. Okay. Does that kind of make sense? Pick a point, change it, pick the next point, change it, connect. Pick the next point, change it, connect. Because some people will have the wrong shape because they connect the 3 points after and it's wrong. All right? When you're done, you're going to flip over. Okay. What's this one doing now? Reflection in the y-axis. Now, how do I know that? Because it's with the x. So that is affecting x values. When it affects x values, it's a reflection in the y-axis. Okay. Back to grade 10. Does everyone have that? In grade 10, if your teacher gave you this, there was sheer panic ensued in the class. They're like, huh? And your teacher's like, don't worry about the f of x, it's just a y. It's just a y. So they say to you. But you need it for function notation. So if they gave you like f of 2, you did what? 2 went in for the x. So you went 2 And then you did the good old replace, like you do a tire. You take this one out, put other one in. You don't put it on top of it. Take the x out, replace it with a 2 plus 1, and you would say 5. Okay? F of 2 equals 5. And you actually found a coordinate. Your input was 2, your output was 5, and you got a coordinate 2, 5. Every single time you did that. Input, output. Right? Then your teacher was like, wait a second. It gets better. And they said, hey, what if instead I said f of a? Then what would you do? Put a in for x. That's it. So instead of having 2x plus 1, I would have 2a plus 1. True? Nothing crazy about that. Makes sense, right? Okay, so when we go to this example, and it says f of negative x, what would you do with that? Put the negative x in for all the x's. So if there's one x, it goes in for one x. If there's more than one x, it goes in for all of them. This one happens to have 2. You see that? So it's going to go in for both. So I'm going to say y equals, because y equals f of negative x, so I'm going to get negative x squared minus 4, and then this x gets ripped out, negative x plus 4. You see that? Does it make sense? I'm taking out every x and replacing it with negative x, just like in the previous thing we talked about. The x got replaced with an a. If I had had more than one x, I would replace them all with a. Okay, what happens when you square a negative? It becomes positive. So we actually end up with y equals x squared. And then negative 4 times negative x is positive 4x plus 4. We're not going to graph them because it's on a Friday, but can you put them both into your calculator? So into y1 and into y2, and I want to show you something cool. What's up?
Is the one x still be negative, like behind 4?
You're multiplying them.
Oh,
Negative 4 times negative x, positive 4x. Put the two terms together. Yep. Into y1, your original. I'm going to show you something fancy about your calculators again. If you have the colored ones, I'm not going to teach you anything really that fancy. X squared plus 4x plus 4. Yeah? Guys? So, this one goes into your calculator. This one goes into your calculator. If you have the ones who give you like a red and a blue graph, cool. You're in a better boat. You don't have to pay attention. Well, you thought you were in a better boat, but you're not. These guys can be in a kind of, everyone else can be in kind of the same boat. So, paying attention? If you go to look at the left of the y, there's like a line like this. Leave that one. Go to your y2 and go to that line. It's a slanted line. Just hit enter once and stop. Now everyone put down your calculators. I'm going to ruin this for you so that for the next 10 minutes, there are not people in this class trying to figure out what they all do. If you hit enter once, it gives you a thick line. So when you draw your graphs, your first graph will be the thin line, your second graph will be the thick line. Did you know that your graphs draw in order? So if you have more than one graph, they draw in order. However, once they're drawn, everyone paying attention? Calculator sound? Once they are drawn, you can't tell which one's which anymore unless you kind of have some idea of it. So if you make one thin and one thick, you can tell. Your first one I always make thin, your second one I always make thick. Once they're drawn and you press graph, they don't redraw themselves first, then second. So unless you make one thick and one thin, you can't tell unless you have the colored calculators. Now, if you don't do this, if you press it again, you're going to get this key thing. It just shows like little keys. Press it again, you get a dashed line. You get a dash. If you press it again with a shaded thing, it shades below and above. That's all it does. So don't spend the next 10 minutes pressing every button and looking to see what they all do. I just ruined it for you, so that you please don't do that. There's going to be one person who's going to ignore me for the rest of the class and be testing out all the things inside that thing. That's your choices. I've laid it out for you. All right. So please go to this one and hit the thick, hit enter once, and then press graph. So whenever you have more than one graph, it can do that. If you have the colored ones, that's where you can change the color. So if you're colorblind, honestly, I would not pick red or green. or whatever color you have problems with. Pick a different color, right? Yes? Okay. So, you can see what's happening on that graph. The graph that's in front of you. There's a reflection in the y-axis. Where's the invariant point? On the y-axis. What's the coordinate on the y-axis? Remember we had the same graph over here. What's the coordinate on the y-axis? 0, 4. So, invariant point is 0, 4. And where do the invariant points exist? On the y-axis. What are the x values on the y-axis? 0. Since the x values are 0 and multiplying by -1, will still be 0. And then how does the graph of y equals f of negative x compare to y equals f of x? We have a negative x, so it's a reflection in the y-axis. If this wasn't a Friday, we would be sketching the graph, but it's a Friday. Okay, so on this one, sketch the following reflections. This one's a reflection in the what? Reflection in the x-axis. And what does it affect? The y. So my mapping is going to be xy becomes x what? Negative y. And my x has stayed the same because my x is just an x, right? And what is b? Reflection in the y-axis. And what does it affect? The x values. So I want you to take these coordinates, 1, 2, 3, 4, 5. This one can be important too. So could this one be, because there'll be invariants on different ones. And sketch the two graphs. 1, 2, 3, 4, 5, 6. Negative 6, 0. It can become negative 6, 0. Is that one staying? Makes sense because it's reflection in the x-axis and whatever axis it's reflecting in. If it's only doing that, it will remain invariant. And I have 1, 2, 3, negative 4, 1, 2, 3, 4, 5, 6. Negative 4, 6 is going to become negative 4, negative 6. And then negative 1, 6 is going to become negative 1, negative 6. Next. This will remain invariant. Ooh, that is not a straight line. I'll pretend it is. And then 1, 2, 3, 4, and negative 3. It's going to become 4, 3. Oh my goodness. I just can't. Then when I apply it to this one, I'm going to get negative 6, 0. It's going to become 6, 0. So it's here. And then negative 4, 6 is going to become 4, 6. And then negative 1, 6 is going to become 1, 6. This remains invariant. And then we have the rest of this one, 4 and -3. So 4 and -3 becomes -4 and 3. And then 7 0 becomes -7. Yeah? Okay. All right, so we will be finishing the rest of this. It's just a couple examples on the back, and then doing stretches as well on Monday. So if you want to start on the homework, you can. You have it, right? There's the horizontal translation, and then there's the stretch homework. You can start working on that as well, because it'll end up being due. If you don't start it today, you'll have the stretch and the stretch. Sorry, you'll have the reflection and the stretch on Monday. So I have to do the reflection homework. And stretch. Reflection homework. And stretch.